Welcome to The Explainer. Today, we are cracking the code on a critical standard that keeps our world safe from some pretty invisible dangers. We're talking about the ASME Pressure Change Test. And ASME, of course, is the American Society of Mechanical Engineers. This procedure is the real deal. It ensures the integrity of everything from massive power plants to complex manufacturing facilities.
Okay, let's just dive right in. Here's the roadmap for today. First, we're going to talk about why we even need a test like this in the first place. Then, we'll get into what the test actually is, walk through the all-important planning phase, check out the required gear, detail how you run the test, and finally, figure out what it all means, how we get that pass or fail verdict.
All right, first things first, let's set the stage, because to really get this, you have to understand why a tiny invisible leak can be such a huge deal. I mean, think about it. We are surrounded by pressurized systems every single day, and we don't even think about them. Gas pipelines running under our streets, chemical reactors, even the HVAC systems in giant buildings. So the big question is, how do we know, for sure, that these systems are sealed tight and aren't about to cause a huge problem?
You know, the basic idea here is actually pretty simple. It's like having a slow leak in your car tire, but just blow that up to an industrial scale, where the stakes are so much higher. It all comes down to proving that a system can hold its pressure over time. Because a tiny, undetected leak in the wrong system could mean lost money, environmental damage, or honestly, something way worse.
So, that brings us to the official solution. Let's see how all this concern gets channeled into a standardized, repeatable procedure that industries all over the world absolutely rely on.
And here it is, the formal definition straight from the ASME standard itself. The key phrase here is determining the leakage rate. See, it's not just about a simple yes or no question of, is there a leak? It's about precisely measuring how fast it's leaking by watching that pressure change. It's methodical, it's data-driven, and it's super reliable.
But here's the thing. You can't just show up with a pressure gauge and call it a day. The standard makes it incredibly clear that the whole thing, the entire test, hinges on a rock-solid, documented plan. And you have to have that before you start.
And when I say clear, I mean it. This isn't a suggestion, it's a hard and fast rule. A detailed written procedure is the first mandatory step. It's what ensures every test is consistent, repeatable, and, most importantly, safe and accurate. No procedure, no test. Period.
So what exactly needs to be in this plan? Well, the standard boils it down to these 4 pillars. You have to spell out the exact test pressure, say exactly how long the test is going to run, define how often you'll be taking readings, and, this is a big one, state the exact acceptance criteria. That's the line in the sand that determines a pass or a fail. Now this is where it gets really interesting. The ASME standard goes even deeper and classifies every single part of that procedure into one of 2 buckets, essential or non-essential. And trust me, understanding the difference between these two is a very big deal.
Okay, so here's the key difference. If you change a non-essential variable, something like the specific cleaning technique you use or which qualified person is running the test, you just have to update the paperwork. No big deal. But if you change an essential variable, like the test pressure or the duration, bam, you have to scrap it and completely requalify the entire procedure from scratch. It's the standard's way of ensuring nobody cuts corners on the things that actually affect the outcome.
All right, so our plan is written, it's approved, it's ready to go. Now let's talk about the hardware, because to get results you can actually trust, you need the right tools for the job.
And yeah, the standard is very specific here. You can't just grab any old gauge. For pressure, we're talking about accurate tools like digital indicators, or even high-precision quartz Borden tube gauges. And just as important is temperature, so you'll need accurate instruments like dry bulb or dew point sensors. Whatever you pick has to be accurate and sensitive enough for your specific test.
And this right here, this is the golden rule of measurement. It is a non-negotiable. Every single instrument you use, your pressure gauges, your temperature sensors, all of it, has to be properly calibrated against a known traceable standard. Why? Because an uncalibrated gauge is basically just guessing. And in this world, guessing is simply not an option.
So now, it's time for the main event. We have our plan, we have our calibrated gear, it is time to actually run the test.
And you really have 2 ways you can run this test. You can either apply pressure, pumping the system up to a pressure above the atmosphere around it, or you can do the opposite and pull a vacuum, taking the pressure below atmospheric. The method you choose just depends on what makes the most sense for the system and the test requirements.
The process itself is very methodical. First, you apply the pressure or vacuum. Step 2, and this is super important,
You wait. You have to let the temperature in the system stabilize, because temperature changes can mess with your pressure readings. Once it's stable, you log your starting numbers, hit the stopwatch, and then start taking readings at the intervals you set in your plan, which can't be more than 60 minutes apart.
And of course, size matters. The standard knows that a small pipe is going to behave differently than a giant storage tank. So for small systems, there's a simple rule. Wait a minimum of 15 minutes for the temperature to stabilize. But for large systems, you can't just use a timer. You have to actively measure and prove that the internal gas temperature has stopped changing before you can officially start the test.
Okay, the test is over. We've collected all our data. It's time for the moment of truth. Let's talk about how we get to that final verdict, pass or fail.
After all that careful work, the final judgment is actually really straightforward. You take the pressure change you measured over the whole test, and you compare it to that acceptance criteria you defined way back in the planning stage. If your pressure change is equal to or less than that number, congratulations, you passed. If it's more than that number, the test is a fail. It's that simple.
So, what happens if it fails? Well, the process is just as clear. Step 1, you have to go on a hunt and find the source of the leak. Step 2, you make the repairs. And step 3, this is the critical part, you have to run the exact original test all over again. No shortcuts, no changing the rules. You have to prove that your fix actually worked under the initial test conditions.
When you really step back and look at this whole standard, the biggest insight isn't just about the procedure, it's about the overwhelming emphasis on planning. That old business with essential variables proves that the foundation of a safe, reliable test is built long before any pressure ever gets applied. It forces you to be meticulous. So that leaves us with a final thought, right? If just a tiny change to one of those key variables means you have to start all over, how does that change your approach to planning?